Okay, so let's get into some calculus. So this is section 7.6, and let's get into some calculus with mass and density. So we said density is just, mass is just the density times the area. Well, so, suppose I'm given, something like, I don't know, we'll take something pretty simple, right? I have that area, and that area will say, there's 0, there's 1. This is some function f of x that is maybe x times 1 minus x, or x minus x squared. And so if I want to find the mass of this, if the density is constant, which is mostly what they seem to deal with here, is they just kind of go with a constant density. So I need that row times the area. Well, we know how to find the area. That's no problem. So our mass is just rho times the integral from 0 to 1 of x minus x squared dx. And so what the heck is that? That's rho times x squared over 2 minus x cubed over 3 from 0 to 1. And so our mass is what? Let's see, x squared, that's 1/2 minus 1/3, so that's 1/6, so we get rho over 6. Okay, so there's mass and density. But now, if we want to do that same idea of center of mass, and say we want to calculate m sub y, well, let's redraw things here again. And remember what we did for m sub y was we just took a given mass and took its distance from 0. And, so here's a given mass, right? Take a slice like that. That's at a distance x. And I just have f of x here. So, times delta x, right? So I get that area. So each of these pieces that I add up each moment, right? So we'll call this xi. Then moment sub I. Okay, I need the mass from that. Well, that was rho times f at xi times delta xi. Okay, so there is the mass, because I took density times area. But then I have to multiply by its distance, so I have another xi. Okay, and of course I'm going to do that with each of these, add it all up between 0 and 1, and what happens is I just get that xi involved, and so my m sub y is the integral from 0 to 1, because again that was from 0 to 1, rho, and x from my xi there, and my f of x, which was what was that? X minus x squared, and then dx. Okay, so what we ended up doing was tossing in that x because of that distance. So we get this m sub y. So this is rho times the integral of x squared minus x cubed dx. This is rho times x cubed over 3 minus x to the 4th over 4 from 0 to 1. And so that's rho times 1/3 minus 1/4, that's 1/12. And so then our x bar, which is equal to m sub y over m, is rho times 1/12 over rho times 1/6. And, well, rho cancels, and 1/12 over 1/6 is 6 over 12, or 1/2. And given the symmetry and so forth, hey, I knew that. Look at the symmetry. Yep, we should have gotten here at x equals 1/2. That makes sense. And so we can find that x bar that way. Okay, we can get our mass, and we get m sub y. And that's pretty straightforward. You know, we just kind of toss in that x in there and go from there. What about the other way around, though? Gosh, what about m sub x? Right? What's going on with that? And, you know, so now as I look at m sub x, let's draw that stuff again. So we've got that. This is 0 and 1. Now m sub x, remember, what we have to do is we have to get masses, and let me put it on pause. Oh, drop my pen. Okay, I had to put you on pause there because I had somebody come into the office. So we are back, and we are asking this question about, you know, how do we do m sub x? And so m sub x, remember, we want distances to the x axis here. And so in this case, where I just have this function, well, what I can do is I could draw that same sort of element, right? So I've got that element, and I can get that same area then. So, you know, the area and then the mass, I still get that same idea of rho times f at some xi. Right, there's some xi. Delta xi, that's the mass. But now, see, I need the distance to the x-axis, and since in particular in this case, since the density is constant and all that, what we'll do is we'll just take the halfway point here. So there's the halfway point. Well, how would we get the halfway point? That would be f at xi over 2. And so we're going to sum up a bunch of things like this from 0 to 1. So our m sub x is an integral from 0 to 1. We've got our rho, have that, and then in this case we have f at our f of x squared and over 2. So I took care of those. They were squared, and then over 2, and all I have left is the dx. And so I get something like that, and we're going to generalize this up in the next video, but so I get something like that. So this is rho, the integral from 0 to 1. Our f of x was, what the heck was our f of x in that case? It was x minus x squared. So we're going to square that over 2 dx. So this is rho 0 to 1. Squaring that thing, that's what, x squared, and minus 2x cubed and plus x to the fourth all over 2 dx. So this is rho, integral from 0 to 1, and we have x cubed over 3, but there's a 2, so I'm going to do x cubed over 6. And then here I've got a minus 2 over a 2, so I really am starting with x cubed. So I have minus x to the fourth over 4. And then finally, I do have a 2 here, and I'll have a plus x to the fifth over, oh, I wrote that. I didn't want that. I wanted a parenthesis. X to the fifth over 10. And that's from 0 to 1. So that's rho, and we have 1/6 minus 1/4 plus 1/10. Gosh, I don't know. Let's see. We can go to twelfths. This is 2/12 minus 3/12. So I've got a negative 1/12. So this is rho 1/10 minus 1/12, I think. And that we can go to 60ths, I suppose. And so that's 6 and 5. So this is rho times 1 over 60. So that was our m sub x. And so our y bar is our m sub x divided by m. And so our m sub x is rho over 60 divided by rho, and what was the mass again? 1/6. So rho over 6. And again, the rho's cancel out. With this constant density, that just disappears, and I get 6 over 60, or 1/10. And you know, does that sound reasonable? I don't know. Well, you know, remember what we're working with here. X minus x squared from 0 to 1. It certainly should be bottom heavy. You know, so I would say it's closer. It should be, you know, closer to the x-axis than half the height. But what is the height? Well, that's at a half. You know, so f of 1/2 is 1/2 minus 1/2 squared, or a half minus a fourth, which is a fourth. And so that's the tallest this is. There is a height of a fourth, and we should be below half of that. We should be below 1/8. Okay, because most of the stuff's down here, wider at the bottom than at the top, and 1/10 is definitely a bit less than 1/8. So I think we did well. So our x bar, y bar is equal to 1/2, 1/10 for our area there of constant density. Okay, so that's the beginning of that. Next, we'll generalize this up a little bit with more than one function. You know, we have this function. You know, I just did one function and bounded by the x-axis. Well, what if in general we're bounded by a couple of functions, top and bottom? And so we'll take a look at that.